And what I'm here to share with you now is an overview of the properties of the unique stellar and planetary environment of M-dwarf stars, and how these properties might impact the habitability of orbiting planets. This is going to prove critical in the years ahead as we keep building upon this exciting list of potentially habitable worlds around M-dwarfs and prioritize planets to target for follow-up by the next generation of space and ground-based observatories. Our planet orbits one single middle-aged star in a galaxy of hundreds of billions of stars, in a universe of hundreds of billions of galaxies. We now know of close to 4,000 confirmed planets around other stars, and many of those, several dozen of which, are of particular interest to those of us in the room, including planets like Proxima Centauri b, the closest potentially habitable world we have, and the planets around TRAPPIST-1, all 7 of which are in the Earth-sized regime, and 1 to 3 of which, depending on who you ask, are potentially habitable. And of course, hot off the presses, LHS 1140b, for which we have both transit and RV data, allowing us to constrain both its size and its mass, which is very exciting. So these planets orbit small, cool, red stars. And many of them orbit in the habitable zone, this region around a star where a planet could be warm enough for surface water to stay liquid, in liquid form. Too close into the star, and the planet is in danger of losing its entire water inventory to space in a runaway greenhouse state. Too far away, and the maximum CO2 greenhouse limit is reached, the point beyond which any further increase in CO2 would no longer be sufficient to keep temperatures above the freezing point of liquid water. But what I am here to tell you, and perhaps the most important take-home message from my talk, is that orbital distance is but one tiny pixel in the rich portrait called planetary habitability. And in fact, the long-term presence of surface liquid water over long timescales is governed by the radiative and compositional properties of the host star and the planet's individual properties, including its environment. But the picture is even richer than I've portrayed it here. And in fact, when we delve more deeply, we see that it looks a bit more like this. So you're not meant to try to read every single box on this slide. What you're meant to do is to feel as overwhelmed as I sometimes feel when I look at this slide. There are a lot of factors and processes that come into play when we talk about a planet's ability to sustain long-term surface liquid water on its surface. So those of us who focus on exoplanet climates have explored many of these areas of impact. And we've done so using observational data that we have for some of these systems, in concert with theoretical climate and other types of computer models. And this unified approach has been critical to allowing us to gain a deeper understanding of the likelihood of certain types of planets orbiting certain spectral classes of stars to be habitable, particularly planets around small, cool, red M-dwarf stars. We're very excited about the prospects for life around M-dwarf stars because, in part, M-dwarfs are so small, they have these low masses, and because of their low masses, they burn their fuel very slowly. They're like the tortoises of the stellar family. And in this case, with M-dwarfs, they live on the order of hundreds of billions to trillions of years, offering lengthy timescales for both planetary and biological evolution, as opposed to the most massive O stars, which are the James Dean of the stellar family. They live fast, they die young, in a few million years, they're gone. That's not very good for biology, given that it's believed to have taken life on Earth on the order of 500 million to 1 billion years to get a foothold on our planet. We're also very excited about the prospects for life around M-dwarf stars because, as has been mentioned, it's easier to detect smaller planets around smaller, lower mass stars with existing techniques, transit and RV techniques. It's also, they offer the best chance of finding habitable planets through sheer numbers alone. And statistics tell us that small planets are more common around smaller, lower mass stars than hotter, brighter stars. But unfortunately, it's not all sunshine and rainbows when we talk about M-dwarf planet habitability. So let's go back to the habitable zone plot here again. You may have noticed that the habitable zone is much closer in to a smaller, cooler star than a hotter, brighter star. And these close-in orbits could pose a number of effects that could be detrimental for planetary habitability, including tidal locking, where the planet's rotation rate is slowed down by the gravitational effect of the more massive star. An extreme case of tidal locking is called synchronous rotation, where a planet's day is equal to its year, and it's always showing the same half of itself to the star at all times in perpetual day, while the other half resides longingly in perpetual night. Would you want to live on a planet like that? Could life survive on a planet like that? It certainly has raised concerns, particularly with regard to the atmosphere, potentially getting so cold on the night side that it completely freezes out. Recently, though, we understand through theoretical models that if a planet has a thick enough atmosphere, it could distribute enough heat from the day side to the night side to avoid atmospheric freeze-out. Additionally, we now know of a possible climatic benefit to synchronous rotation for planets orbiting near the inner edge of their host stars' habitable zones. If these planets have oceans, we could expect a significant cloud layer to build up on the day side of the planet due to strong convection at the substellar point. Clouds are very bright, and these clouds could reflect that incident stellar radiation back out to space, cooling the planet down, essentially buffering it against a runaway greenhouse state, and widening the habitable zone real estate for M-dwarf stars. We also understand, due to recent work, that thermal tides in the atmospheres of M-dwarf planets could, under certain circumstances, be strong enough to counter the gravitational tide and perhaps oppose spin synchronization. This implies that not all habitable zone M-dwarf planets may be synchronously rotating. Another concern that has long plagued the discussion of M-dwarf planet habitability has to do with flare activity. So I mentioned that M-dwarf stars are so long-lived. This has its advantages in terms of lengthy timescales for planetary and biological evolution. It also has its disadvantages. Because they're so long-lived, M-dwarfs have these extended pre-main sequence phases that could last as long as 1 billion years, during which time intense amounts of X-ray and extreme UV radiation could pelt the surface of a planet, potentially stripping away an atmosphere, especially if the planet has a very low, weakened magnetic field. It might be that life would only have a chance of existing at the bottom of an ocean, where it could be shielded from that harmful X-UV radiation. Additional work has explored the evolution of the inner edge of a host star's habitable zone with time. And so what you're seeing here on the y-axis is orbital distance as a function of time. The evolutionary tracks here are for stars of different masses and units of a solar mass. And you can see that for the lowest mass stars, the inner edge of the habitable zone evolved significantly during the first billion years. Planets that we discover today to be comfortably within the boundaries of their habitable zone, their stars' habitable zones, could have been well interior to the inner edge for as long as 1 billion years, during which time they could have lost oceans worth of water to space in a runaway greenhouse state. Furthermore, when those oceans, that water goes up into the upper atmosphere, where it gets photolyzed, the lighter hydrogen escapes to space, the heavier oxygen could remain behind to form these O2-rich atmospheres, which could present false positives for life if observed remotely, especially if the planet is in fact long desiccated. However, as my colleague David Catling will mention after the break, there are some caveats to this argument, particularly when we include photochemical reactions between hydrogen and oxygen. An area that I and my colleagues have made a contribution is looking at the interaction between stellar radiation and a planet's atmosphere and surface, and how that interaction can influence planetary climate and habitability, particularly when we talk about ice albedo feedback and how it might operate a bit differently on M-dwarf planets compared to planets orbiting hotter, brighter stars. So we often think of ice albedo feedback as this positive feedback. Ice is very bright here on Earth, and the more light that ice reflects, the less it absorbs, the colder the planet gets, reflects more light back out to space, temperatures get colder, etc. It's a positive feedback process. But ice albedo has a spectral dependence. So the ice albedo feedback mechanism is going to be sensitive to the wavelength of light coming from the host star. So what you're seeing here is the albedo as a function of wavelength for ice of different grain sizes, ranging from the finest grained ice, which is snow, down to coarse-grained blue marine ice. And you can see both of those end members in this photo. And we've modeled intermediate spectra between those two end members and included a land and an ocean spectrum as well. Ice on a planet orbiting a sun-like star is going to reflect most of the light that hits it, because ice reflects strongly where the sun emits strongly, in the visible and the near UV. However, M dwarfs emit in a very different range of the spectrum, largely in the near IR. And ice on a planet orbiting an M dwarf star is going to absorb much of the light that hits it, because ice absorbs strongly where M dwarfs emit strongly. And after carrying a comprehensive exploration of this phenomenon out, what we understand is when we look at, first of all, setting our planets at equivalent stellar flux distances, using climate models around M dwarf, G dwarf, and F dwarf planets, and then dialing down the amount of light these planets receive from their host stars and observing at what point these planets completely freeze over, we find the M dwarf planets require a much larger decrease in incident stellar radiation to freeze over. Additionally, when we start our planets in globally ice-covered conditions, we find that the M dwarf planet requires a smaller increase in incident stellar radiation to thaw out of global ice cover. And once it does so, it thaws out with a shorter jump in ice line latitude, whereas the hotter and brighter the star, the higher the jump in ice line. What this tells us is that M dwarf planets appear to have more stable climates. They're harder to freeze, and they're easier to thaw. And this could be advantageous for life, particularly life with narrow temperature constraints. So what I hope I've done is given you an overview of the picture, the landscape of M dwarf planet habitability. For a full, complete picture, please see our recently accepted invited review paper on M dwarf planet habitability. Sarah Ballard and John Johnson and I had a ball synthesizing all of the knowledge that had been gained in the last decade since the last review papers of Tarter et al. And Scalo et al. In 2007. But I think my take-home message that I want to leave you with is that there's an understanding that we now have that's realistic, but also hopeful. And that yes, there are certain aspects to the M dwarf stellar and planetary environment that could be challenging for life. There are also aspects that could be quite advantageous for life. And as we've seen here on Earth, amidst a wide range of conditions, life seems to always find a way. So thank you all for your attention. I look forward to a continued discussion.
Thanks, that was really neat. I'm thinking about all those panels you showed and all the things you probably didn't get to talk about. I wanted to ask about one of them. The Earth's magnetic field protects it from the solar wind, protects our atmosphere from the solar wind. You move a planet like Earth much closer to the star, not only does maybe synchronous rotation slow down, maybe weaken that field, but the star's field is very strong. And I wonder how well these hopefully habitable planets we're discovering close to M stars can maintain a robust enough field against the star's field to keep the atmosphere protected from the star's wind.
Sure. Well, it has been proposed that M dwarf planets might need to have on the order of tens to hundreds of Gauss in terms of their magnetic field to avoid things like the coronal mass ejections from their parent stars. But it's under debate. The likelihood of an Earth-sized planet having that strong of a B field is questionable, but it's certainly something that we need to do a lot more modeling work on to accurately get a better understanding of what the likelihood, the range of magnetic fields we can expect from M dwarfs.
There is an aspect of climate stability that you didn't mention, which is the existence of a moon. For the Earth, it was quite important for maintaining the spin axis in a stable configuration. And there is an underappreciation of some studies that were done in the literature that stars below half a solar mass basically cannot, in the habitable zone of those stars, the planets cannot retain their moons. And so, do you have any comment on the importance of the moon for life?
Well, I've read a number of papers that are still debating this idea of how important the moon really is to stabilizing our planet's obliquity. There certainly have been papers that imply that it's very important, and others that imply that without a moon in certain computer simulations, the obliquity oscillations are actually not as large as we once thought they would have been. So I think it's still up for debate as to how necessary a moon is. I certainly think moons are great, but they may not necessarily be pivotal to stabilizing obliquity and mitigating obliquity oscillations over long time scales.
Hi, David Kipping from Columbia University. Yeah, I should talk about moons, I guess, but I won't. I'm going to ask you something else.
That's right.
So,
it's the exomoon guy right here.
Yeah, so I guess we know that there are so many of these M dwarfs, as we've heard about. 3/4 of stars are M dwarfs. They seem to have plenty of planets, as Courtney showed us, plenty of Earth-like planets, maybe even more than Sun-like stars. And they live for so long, like trillions of years. And from your talk, we're hearing how the climates may also be more stable, in fact, than planets around Sun-like stars. So I just wonder if I could get you to comment on the idea that this kind of implies that we are very special, does it not? That to live around the star that we live around. So how do you feel about that?
I like being special. And there's certainly, I come from the University of Washington, where there's a couple of professors who wrote an incredibly interesting book called Rare Earth. I'm of the opinion that given the statistics that we've heard from Courtney and others, that if it is just us, it would be highly improbable. Especially looking at the diversity of life that we have on the Earth. I mean, we know that life requires energy, but not necessarily stellar energy, because we have life at the bottom of the ocean in hydrothermal vent communities. And in little crevices and cracks and amidst incredibly desiccated environments and high radiation environments. And so there seems to be ways, we know that life, every single type of life on the Earth requires liquid water in some form, and that's one of the reasons why liquid water is what drives our search out for life elsewhere. The likelihood of liquid water on a planet's surface certainly could be harder to constrain, but just looking at our planet, I feel like that it's unlikely that we are as rare as some of us might think we are. So. Oh, sorry, I should go over here. You're next. It was here.
Dimitar Sassel of Harvard Origins of Life Initiative. A very nice and deep talk, Aomawa, but I just wanted to make a point with my hat, somebody who talks a lot to chemists and biologists. They also care about something else which we usually imply but don't explicitly talk about. That is the planetary environments to sustain life versus planetary environments to allow life to emerge. That is the chemistry to life transition before there is adaptability and need for long-term sustainability given those conditions. Mm-hmm. And that appears to be, we don't know either of them very well, but that appears to be a more restrictive set. So it adds on to our target selection as to trying to figure out which of those systems would have also allowed for that chemistry to life to emerge in the first place, and then look for those.
Thank you for that point. Yes, we do know one of life's requirements, besides liquid water and an energy source, is the basic building blocks, a suitable environment for the basic building blocks of life in some form, right? Sulfur, phosphorus, oxygen, nitrogen, carbon, hydrogen, sponge for short. So we do need that. And in terms of the landscape of planets, we know that terrestrial planets sort of by nature have an energy source along with the basic building blocks in some form, but whether it's the right form is certainly important.
Michael Meyer, University of Michigan.
Yes.
Just to come back to this issue of how special we are, I go back and forth on this in my own mind, but we have Jupiter and Saturn as well, outer gas giants, and this may be something we need to take into account. There's a lot of debate, and I don't want to get into a technical discussion of it, about whether these rocky planets form dry and hot, as some people think, or whether they can sequester enough water so that later, when it can exist in liquid form on the surface, it's there or not, and whether we need gas giant planets to help or maybe even hurt that process. So I just wanted to raise that because I think we all, or many of us agree that the frequency of gas giants around M dwarfs is much lower than it is around FGK stars. So maybe we're not so special taking that extra factor into account.
Sure. And I'm glad you mentioned the sort of the volatile question, because one thing I meant to mention is something that could mitigate this sort of fate of runaway greenhouse states for planets in the habitable zone due to that extended pre-main sequence phase is if you have planets that have started beyond the snow line, where they have essentially water to lose, and then they migrate in, and therefore they could actually still have a chance of remaining somewhat wet, even with that extended pre-main sequence phase in the runaway greenhouse. So yeah, volatile inventory is crucial. One more question. Zach.
Thank you, everyone, for this wonderful talk, and for your, sorry, Zach Berta Thompson, CU Boulder. Thank you for this wonderful talk and for your review paper, which is incredibly helpful. I wanted to ask about the outer edge of the solar system, the outer edge of the habitable zone, thinking about LHS 1140b, a Mars that is 70 times more massive. I'm curious for your thoughts on what the danger of a snowball Earth state is for that system, and thinking about it in terms of with perhaps a more substantial greenhouse.
Yeah, so I'm super excited to work on this planet that you've co-discovered. Certainly, given that low insolation, I think you said 40% of what Earth gets from the sun, it would need to have a significant greenhouse gas envelope. CO2 is one of those greenhouse gases that we talk a lot about. That's why we have that sort of maximum CO2 greenhouse limit. We assume that if a carbonate-silicate cycle operates on exoplanets, then we would expect CO2 to build up as temperatures go down and precipitation goes down, CO2 builds up in the atmosphere. However, because of this maximum CO2 greenhouse limit, I believe that LHS 1140b it's within that limit, so it's still in the habitable zone. But other forms of greenhouse gas heating have been discussed, like using H2. And it's, as a non-condensable greenhouse gas, it would actually you'd be able to push that limit even farther. So that's an idea. And then the issue too is the dry environment. So we're working on looking at alternate surface types that might be possible out there in the outer edge, and that could have their own radiative properties, which could have implications for climate. So I look forward to spending more time on this planet in particular.